What's going on, math people? All right, we're back, and today we're going to be finding the inverse of functions. All right, so there's something that we need to know about functions before we can find the inverse. In order for a function to be invertible, it must be one to one. Now, how do we determine if a function is one to one? A function is one to one if it has no repeating output values. We know that a set of data is a function if there are no repeating input values. So no repeating input and no repeating output gives us a one-to-one function. Let's go ahead and jump into this. All right, so we look at the first set of data. All right, it says determining whether a function is one-to-one. Looking at the column, we're focusing only on the output when we're determining one-to-one because it said it's a function. Determine if it's a function. So we know it's a function. So we need to check to see if these outputs repeat. What's happening right here with this 38? It's happening more than one time because 55 is going to it and 61 is going to it. That's a repeat. Since we have a repeat right there, this is not one-to-one. All right, so part B, we have another set of data. We know it's a function because it says determine if it's a one-to-one function. Now we're going to check these outputs. Checking the outputs, see if any repeat. None of the outputs repeat, therefore that function is one-to-one. I know it's too easy. Let's keep going. Using the horizontal line test to determine if a graph represents a one-to-one function. Now, the horizontal line test simply says if you draw a horizontal line, boom, that is a horizontal line that goes left to right, and it intersects the graph at most one location, then that is a one-to-one function. Let's play around with some graphs. Boom, that right there is a failure. There's an intersection there, therefore that is not one-to-one. Not one-to-one. All right, so then it says test these functions out. We have the function, the square function, also the quadratic function. We know that the graph of that guy happens like so. Let's run the horizontal line test and see what happens. Whoa, we have a oink oink right there. That means it's not one-to-one. And then we have the graph of the cube function. And the cube function happens something like so. Hey DJ, run that horizontal line test for me one more time. One time. One time. One time. As long as you draw horizontal lines and they happen at one location, intersect the graph at one location, then you have a one-to-one function. All right, let's keep rolling. Determine the inverse of a function defined by a map or a set of ordered pairs. If a function is one-to-one, this is what we said earlier, the function has to be one-to-one, then it has an inverse. And all the inverse is swapping the data, okay? So to find the inverse, we interchange or swap the elements of the domain, which is the input, with the elements of the range, which is the output. So we have x, y, and let's say the input for x is 1, 2, 3, and the output for y is 4, 5, 6. And let's call this function f. Now, the inverse is denoted by putting a -1 at the top of the function and swapping the elements of the domain and the elements of the range. So the input for the inverse would be 4, 5, 6. And the output for the inverse would be 1, 2, 3. So you can see what we have is the domain. This is something you'll need to know. The domain of the inverse function, of the original function, equals the range of the inverse function. Just look at the elements. The elements for the original function is 1, 2, 3. The range for the inverse function is 1, 2, 3. And likewise, the range of the original function equals the domain of the inverse function. That'll save you a whole lot of time. All right? Moving on. I remember when I first saw this bubble, this glob of stuff, all of this. I was like, what? But basically this information says exactly what we just explained on the last slide. The domain of the original function is the range of the inverse, and the range of the original equals the range of the equals the domain of the inverse. All right, so it gives us a one-to-one function, and it wants us to write the inverse function. So this is your original function. The inverse function. The inverse function would simply be for your input on the inverse side, population to state. And you just put all the data and just swap the data. That's all it's saying to do. Hold on, it said something else. Go back. Then state the domain and the range of the inverse function. The domain of the inverse function is all of the data that's under population. The range of the inverse function is all of the data that's under states. This says find the inverse of the following one-to-one function. So it told us that it's one-to-one. Therefore, we know it has an inverse. So the inverse, we'll call this original function f. We'll call the inverse function f inverse. And the inverse is easy. Just swap each of the elements. Just go through and swap those elements. Boom. It doesn't matter if the values are the same for the x and y. You're still swapping elements, baby. Still swapping them. And finally, we get here. Bow. Now, it says, what is the domain and range of the function and its inverse? All right, so the domain of the original function up top, the input values or the x values. And that is, but we can let's do this real smooth. Let's do this real smooth, right? What we're gonna do is save ourselves some time so we don't have to write this more than once. We're gonna use some information that we already know. If I can get the screen to come down and give me my eraser. No, that's not what I wanted. That's not what I wanted. Thank you. Golly, making me look like an amateur. We know that the domain of the original function equals the range of the inverse function. So we're gonna just two birds, one stone. Domain of the original function, -5, 3, 0, 2, 7. Is also the range of the inverse function. We also know that the range of the original function is equal to the domain of the inverse function. And we have 1, 3, 0, -4, -8. Just like that, we handle business. All right, now finding the inverse of a function. Verifying inverse and finding the inverse of a function. Now, the way you verify, the way the textbook wants you to verify, I'll say it like that, is by taking the compositions of these functions. What do you mean compositions? We ain't did that in a long time. Well, it's just recalling information. Plug in a function inside of a function. So we're going to take the function g and plug it in and plug g inverse inside of it and see what we get. So we have the function g is x cubed, so I'm going to put the g inverse function inside of that. That comes out to equal x. We're going to do the same thing with g inverse. We're going to plug g inside of g inverse. G inverse is cube root. So we're going to plug in x cubed, and we get x. Since both compositions produces an x as its final solution, those are inverses of each other, and we just verify the inverses. Same thing for part B. F of f inverse equals 2 plus 3, and then we're going to go and put 1/2 times x minus 3 inside of that function f. And that gives us 2 times 1/2 is 1 times x minus 3 plus 3 equals x. Do the same thing for f inverse of f of x. So this time we're going to take 1/2, and then where the x was, just so y'all can see the difference, I'm inputting the f function, and I'm going to simplify. So we have 1/2 times 2x equals x. Again, both compositions came out to equal x. Therefore, inverses are verified. Now, how do you go about calculating the inverse itself? Algebraically determine the inverse. So, algebraically determine inverse. Let's get us some goodies. So we have 1, rewrite the function, whatever the function is, as y. Swap x and y. Solve for y. Once you get that y by itself, you have officially gotten your inverse. So in this example, we have f of x. F of x equals x cubed minus 7. So the first thing we said to do is rewrite f of x as y. So we have y equals x cubed minus 7. Swap x and y. X equals y cubed minus 7. Solve for y. Meaning get y absolutely alone. We have x plus 7 equal y cubed. To undo that cube on that y, we'll take the cube root of each side. And we have cube root of x plus 7 equals y. So that tells us f inverse of x is equal to the cube root of x plus 7. Every time. All right? Takes a little practice. Do a few examples, okay? All right. Again, same thing. We're going to rewrite f of x as y. We have y equals 2x plus 1 over x minus 1. Swap x and y. X equals 2y plus 1 over y minus 1. Solve for y. We're going to have to cross multiply. So we have x times y minus 1 equals 2y plus 1. Distributing, we have xy minus x equals 2y plus 1. Everything that has an y in it, get it on one side, and everything else that does not have a y on it, put it on the other. So we're going to bring that 2y over. You need to be over there with your other y. So we have xy minus 2y minus x equal to 1. That x that's on that left-hand side, you don't have a y attached to you. So move on over. So now we have xy minus 2y equal x plus 1 equals x plus 1. Factor y out. Because remember, we're solving for y. We're getting it by itself. finally, guess what, team? Now that we have this y all alone, you have found your inverse. And we have f inverse of x equal to x plus 1 over x minus 2. This x cannot equal 1 at the top simply means that 1 is not in the domain. Looking at the denominator for your inverse, x cannot equal positive 2. All right, keeping it rolling. Last example. Oh, it says restricted domain. And the reason why it says restricted domain, remember, we ran the horizontal line test on this function earlier, and we said it's not one-to-one. And we also said that in order for a function to be invertible, it had to be one-to-one. But let's say if we restrict the domain, and here's the y-axis, and it says I want all values of x greater than or equal to 0. So it's only focusing on this side. Now, if you draw a horizontal line through that, you're going to be one-to-one no matter where you hit. So that's what it's talking about, the restricted domain for this function. And this is an easy problem. We rewrite f of x as y equal x squared. Swap x and y, x equal y squared. Solve for y, square root of x equals square root of y squared. That's simplified, equals. And finally, we have our inverse function, f inverse of x equals square root of x. That's inverses. All right, team, my math people. See you next time.